Okay, so this unit we're working on our fundamental counting principles and learning about permutations and combinations. These are different fancy words that we use for having a bunch of different things and arranging them sometimes in order, sometimes in collections, sometimes in groups or subgroups. And we're doing this, of course, to emulate something that could be happening statistically as time goes by. But we're kind of taking a break from statistics. I'm working more specifically on fundamental counting principles. So in your course, you may be starting with this right away, or you may be starting with this sort of part of the way through the year. But either way, we'll be doing probability after this. And the reason why we learn how to count is so that we can effectively find out the probability of specific instances happening. And those specific instances often have orders and things like that. So that's really what we're going through now. So we start with a scenario here in our very first introductory section. The introductory section is called organized counting. Okay, and we're going to learn two fundamental counting principles. These are things or ways in which we can do fast counting without having to do a lot of drawing or mapping. Okay, so we'll start with where it all comes from. And the technique that sort of shows us our first fundamental counting principle, which is the multiplicative principle. But either way, here's the scenario. Okay, Lisa, a student at Loyola, must decide what she's going to wear. Her choices are, well, she doesn't have a choice with her shoes. She has to wear her black shoes. But she has a choice whether she wears her pants or her kilt. She also has a choice as to whether she's going to wear her vest, a sweater, or a pullover. Okay, and she also has to choose whether she's going to wear a turtleneck, a polo shirt, or a button-up shirt. So which one of those, okay, all 1, 2, 3, 4 things make a complete outfit. So you may have learned how to do this when you were in grade school and learned how to draw these things called tree diagrams. And tree diagrams basically sort of branch outwards. And when you get to the end of the branching, those are all the possibilities or possible outfits or possible circumstances that could exist when you finish the whole process. In my other class, sometimes I start with a note on picking a combo from McDonald's, okay, where you start with a sandwich and then you decide on the size of your fries, then you decide on a drink, and before you know it, there's a whole bunch of possibilities that you could have there. So a tree diagram will element you choosing a combo. In this case is to choose an outfit. Okay? So in this instance, we have one choice to start with, black shoes. And a lot of people even draw a little line coming out like that towards the first choice. Whenever there's a choice, it branches outwards into those two choices. Okay? And it sort of feeds from one to the next, to the next, to the next, because we're doing this and this and this and this, and all of those elements are together in choosing an outfit. It actually doesn't even matter the order that she does it in. She could choose her shirt first, or choose her bottoms first, or choose her sweater first. In the end, it'll still come out as the same number of options in the end. So we map out this possibility. So we start with black shoes, which is only one choice, and then we say, okay, well, gray pants or kilt. So she can go black shoes and gray pants, or black shoes and kilt. And so it branches out into two possibilities, which means according to her shoes and her bottoms, she can have two outfits. Then, of course, once we add more things to her outfit, the top part, then, of course, there's going to be more possibilities there. She has 3 different sweaters to choose from, okay, a vest, a sweater, or a pullover, okay? And from the gray pants, if she goes with black shoes and gray pants, there's 3 options that branch out from this option. Those 3 options can also exist for the kilt. So we actually have 3 and then 3 branching outwards. So my first choice, there was no choice, so there's 1. Second choice, there was 2 choices, so now 1 turns into 2. Third choice, there's 3 choices, but rather than having 1, 2, 3 outcomes, we have 1, 2, 3, 4, 5, 6 different outfits. And that's because we have 3 outfits to go with this branch and 3 outfits to go with this branch. Okay, finally we choose an undershirt to go along with this sweater, and it's either a turtleneck, a polo shirt, or a button-up shirt. Okay, now we don't go back to the beginning. She's not choosing her black shoes or a top. She's choosing this and this and this and this all together to form one outfit. So it's branching outwards and becoming more and more possibilities. So if she chooses black shoes, gray pants, and a vest, she still has 3 options for the undershirt that she can have. Okay, if she chooses black shoes, gray pants, and a sweater, she also has the 3 options. When you look at all the combinations, these are all different, distinct outfits. And as a result, even though they're slightly pretty much the same thing, the overall result is going to be a different outfit. And so we ask ourselves how many outfits there are. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. And you can follow along this line of thinking to actually see what that outcome looks like. In this case, the outfit is black shoes, a kilt, a pullover, and a button-up shirt. Okay, and that creates an outfit. She had one choice over here, and then she had to make a choice for two possibilities over here, and a choice for three possibilities over here, and a choice for another three possibilities over here. Okay? Now, it's not 1 plus 2 plus 3 plus 3. It's not 1 or 2 or 3 or 3. She has to choose black shoes. She has to do this choice, and she has to do this choice, which is, this is a bottom. This is shoes. Not really a choice because she doesn't have a choice. And she has to choose a sweater. And she has to choose an undershirt. And in the end, she has to choose all of these possibilities to create a single outfit. The result is 18 different outfits in total. Now, how do 1 and 2 and 3 and 3 work together to give you that 18? Well, we can see that it branches out. As it branches out, it multiplies possibilities. So when we actually use this principle, okay, if a task or a process is made up of stages, you know, in this case, different choices for different pieces of her outfit, with separate choices, the total number of choices is actually the first number of choice and the second and the third, and then it's multiplied between each one. So the star is representative of multiplication. So it's, again, one choice and two choices and three choices and three. Again, one type of shoe, two types of bottoms, three types of sweaters, and three types of pullovers. The and confounds it. It multiplies it. So whenever you're doing something and something and something and something, you actually end up multiplying things together. So in the end, you multiply them all together and you get 18 ways, or 18 different choices, or 18 different outfits, or 18 different combos. Okay? And in this case, the multiplicative principle works really well. If you wanted to pick a combo at McDonald's, let's say you have three favorite sandwiches. So you choose your sandwich first. And then there's two sizes of fries, medium and large. And then there's, I don't know how many drinks there are at McDonald's. Let's just say there's 10 different drinks. Then, you know, the number of different combos you come out with, where at least one of those elements is different from each other, is 3 times 2 times 10. That means 60 different combos. Again, it doesn't relate to this question at all, but it still relates to the fundamental counting principle, not to Sarah's outfits. This would be combos at McDonald's. Okay, so it depends on the situation that you're looking at. That, again, is just I'm just spitballing a possibility here. So let's look at another situation. Martin lives in Mississauga and wants to travel to Egypt. To get there, he first must go to the Toronto airport. Then the cheapest way was to have a stopover in England. Okay, so he's going to get to the airport, then he's going to go from Toronto to England, and then England to Egypt finally. Okay, he finds out that there's 3 flights that are available from Toronto to England that he could take. There's 2 flights available from England to Egypt, and he can get to the airport by bus or by taxi. Okay, so we start with, maybe you go in order, you don't have to go in order, but he has to get to the airport, and then he has to get to London, and then he has to get to Egypt. Okay, so there's 2 options, bus or taxi, to get to the airport. Obviously, it starts at home. Okay, 2 options to get to the airport, and then there's the 3 flights that he can choose. That, of course, as you can see, goes 2, 3 possibilities from the bus, 3 possibilities from the taxi, or 1, 2, 3, 4, 5, 6, or 2 times 3 is 6. But we still have another flight to take. He's got 2 flights that he can take. Once he gets to London, there's 2 flights that he can take in order to get him to Egypt for his particular journey. And so as a result, there's 2 outcomes, 2 outcomes, 2 outcomes. Oops, I forgot to put that. Flight 2. Okay, and as a result of ways to get to Egypt from his front doorstep, there are 2 times 3 times 2, or 2 to get to the airport, and he has to get to London, and he has to get to Egypt. And so 2 times 3 times 2 ends up giving me a total of 12 different ways he could get to Egypt. Okay, now that's the overall process. This is like a combo at McDonald's. There's your sandwich. Okay, 2 different sandwiches that you like. There's 3 different sizes of fries, and there's 2 different types of drinks that you like. And these are all the different combos you can get. So it's the same thing. Again, when you're doing one thing and another thing and another thing and another thing, and you view the process in and of itself all together, then it's going to be a multiplication scenario. Okay? And that's our multiplicative fundamental counting principle, or we like to call this the AND rule. Okay? If that's the case, again, that's something that you're going to get used to, and you're going to notice those patterns as we go along. Okay? Now, the whole point of this process is to get away from doing tree diagrams and going towards doing things other than that. Because if we have a lot of possibilities, okay, let's say I have to pick 2 students from the class in order to present first and second, then there's 30 people in the class. That would be a difficult tree diagram, because what would happen is there would be 30 students that would branch out for the first choice, who presents first, and then there'd be 29 students that would branch out for the next choice. Okay? And so as a result, to draw that as a tree diagram is stupid. So we want to try and be able to use these fundamental counting principles instead of drawing a tree diagram. But what we're really doing is drawing a tree diagram. So here we have a simple scenario. There are 12 chess pieces in a bag. Okay? The types of pieces are queens, kings, knights, bishops, rooks, and pawns. Okay, and those are all the different types of pieces that are in a chess set. We usually have more pawns than 2, but everything else is usually in 2s, and they're in blacks and they're in whites. One from one side and one from the other side. Oh wait, there's pairs of other things, I should say. Yeah, so anyway, this is just a circumstance. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 chess pieces in a bag. So you throw them into a sack. Remember, you've got 2 queens, 1 white, and 1 black. And you've got 2 kings, 1 white, 1 black. You've got 2 knights, 1 white, 1 black. You've got 2 bishops, 1 white, 1 black. You've got 2 rooks, 1 white, 1 black. You've got 2 pawns, 1 white, 1 black. What you do is you shake the bag. And then you take out 1 piece. Take it out, put it on the table. There it is, just sitting there. Okay? The bag is then shaken, shaky, shaky, shaky. And you've got 11 pieces left in there now. And then you take out another one. What I want to find out is how many different ways could that end up where I have those 2 pieces on the table. One came first and one came second. Okay? So this is the situation that we're dealing with. And of course we could do a tree diagram if we wanted to, but we branch out with 12, and then 11 possibilities would be crazy. So what we're going to do instead is we know we're going to have to choose something first. And then we're going to know we're going to have to choose something second. And we choose first and second. So how many pieces could be chosen first? Remembering that there's 12 chess pieces in the bag. And they're all different from each other. You may say, well, there's 2 queens. Yeah, but one is white and one is black. So they're the queen shape, but one's white and one's black. So they're all different from each other. Okay, so how many items could I take out and put in the first spot? Well, there's 12 items. Black queen, white queen, white queen, black king, white king, black bishop, white bishop, black knight, white knight, black rook, white rook, and then black pawn, white pawn. So there's 12 different elements that are there. And so anything I could take out first. Now, once I take that thing out, it's no longer in the bag. So when I shake it and I take the second thing out, there's only 11 left. And so there's 11 possibilities that could be there. I don't know what they are. I just know that there's only 11 possibilities that could be there. As a result, how many different sort of ways, first and then second, could I take things out of the bag? And it ends up being 12 and 11, but it's branching 12 and then branching 11 from those branches, which we don't want to do. Remember, 12 and 11 is the same thing as 12 times 11, using our fundamental counting principle, because we're doing the first draw and the second draw. First draw and the second draw. And so we end up with 132 different ways that we could take 2 chess pieces out of the bag, if, of course, what we take out first is different than what we take out second. Okay? And so that's how we would do this. We don't want to stay away from tree diagrams. We just want to start using this fundamental counting principle. Okay, so let's try this again. Hopefully, if the first one didn't make sense, the second one will. How many ways are there to select 2 bishops? Okay? So I've still got a first spot, and I've still got a second spot. Okay? And I'm going first and then second. And so both of them are viewed as selecting 2 pieces together. So it's a first and second action. Remember that I've got 12 pieces in the bag. But this is a little different. It's not just how many ways can I do things. It's how many ways can I select 2 bishops. Well, the first time in the bag, there's all kinds of pieces. But amongst them are 2 pieces that are bishops. There's a black bishop and a white bishop. So there's 2 possible outcomes that could be there. You could either have the black bishop or the white bishop come out first. My second is going to be a bishop. But the second one that I take out, even though I'm shaking it around in the bag, I know my second one is going to be a bishop because I'm asking how many ways could I get 2 bishops. And so my second one is also going to be a bishop. But remember, I took a bishop out to begin with. So there's already a bishop right here. Okay, so then what I want to do is I want to take out another bishop, but there's only 1 bishop left. So it's 2 for the first try, and then 1 for the second try. Or 2 and 1, 2 different ways we could get bishops. And we could even name it too, because we can go black bishop first and then white bishop, or we could go white bishop and then black bishop. That's the only way to do it. So we know this is one situation, black then white, and this is white then black. There's 2 outcomes. So our multiplication works along with this. It would be too many for us to count for this way. We'd have to do a tree diagram. It would be too crazy. Okay? Let's try another one. How many ways are there to select a bishop and then a knight? Okay, so I'm going to choose again first and second. Okay, my first choice, I'm choosing a bishop. There's 2 bishops. My second choice, I'm choosing a knight. Now, there's still 2 knights left in the bag. The only thing that's been removed out of the bag is a bishop. I don't know whether it's a black bishop or a white bishop. It doesn't matter. In that first spot, we have a bishop. In the second spot, we're going to have a knight. How many knights do we have to choose from in that bag? Well, there's 2 knights left in the bag. If we use our fundamental counting principle, it's 2, and then we're doing 2 possibilities or 4 ways possible in general. Now you may say to yourself, well, how does that work? Well, I could have a black bishop and a black knight, or I could have a white bishop and a black knight, or I could have a black bishop and a white knight, and I could have a white bishop and a black knight. There's my 4 different outcomes, and that's my 4 different ways. Okay, so again, by creating these little slots for different things that are happening and breaking it up into small little steps, rather than drawing the whole tree diagram, it lets us do things a lot more quickly, this fundamental counting principle. This one's a little trickier, so hopefully you're okay with this. If not, pause, go back, rewind to this point right here where I'm just writing down this example, listen to that one, listen to this one, listen to this one. If you're still having difficulties, ask me about it, but you want to try some of the questions to go along with it as well. Okay, so ask me, we'll meet, we'll figure things out. Okay? All right, so hopefully you're okay with A, B, and C. If you're okay with A, B, and C, now we'll move on to D. All right, how many ways are there to pick a pair? Again, we have to choose one first and then one second. That part hasn't changed. Okay, if we're going to pick a pair, we're not choosing them at the same time. It's just when we take one out and we take another one out, they're going to be the same. Both queens, both kings, both knights, both bishops, both rooks, whatever, both pawns. Okay, you may be able to count them out and figure them all out, but let's see how many ways in which we could do that. Okay, well, what I do know is this. In my first piece, I don't have to worry about who's a pair and who's not a pair. So how many different pieces could I pick for the very first spot? Well, I don't have a pair yet, so anything can come out. So if I chose a black knight, then my second one would have to be a knight. So if I chose a black knight, my second one would have to be a knight. But I could choose a bishop, which means my second one would be a bishop. Or I could choose a pawn, and my second one would have to be a pawn. Okay, so how many different things could I choose in the first spot? And there's 12 different pieces that I could take out in that very first spot. And you're like saying, oh, no, it has to be a pair. Yeah, we'll get there. Don't worry. The first piece, there's no restrictions or limits on it. I could choose anybody, just like I could choose anybody in this spot. What's different is the second one that I choose has to be very specific. If I choose a bishop, a white bishop here, what has to be here? The black bishop. If I choose a white knight here, what has to be here? The black knight. If I choose a black pawn here, what has to be here? The white pawn. So if I choose any of these possibilities here, there is only one match to go with them. And that means that there's going to be 12 pairs. 12 and 1, or 12 times 1, which is going to be 12 different ways, or 12 different pairs. And you may say to yourself, oh, no, there's only 6 pairs. Yes, but it's the order that's important. I can go with a black bishop, and then white bishop, or I could go white bishop, black bishop. And that's just the bishops. right? Because black and white versus white and black are different orders, different circumstances, different scenarios. Again, who I take out first and who I take out second are all those possibilities. And I would do the same thing for the kings, and the same thing for the knights, and the same thing for the bishops, and the same thing for the rooks. So I'd have, 2 for the bishops, 2 for the rooks, 2 for the knights, 2 for the pawns, 2 for the kings, 2 for the queens, and in the end I would end up having 12. I don't want to write them all out because this process takes care of it for me. This is a little bit tougher of an idea. Okay, it's actually something we call an indirect method. So we're learning a lot of things with this one question. So if you don't quite understand that pair one, go back and make sure you understand D. If you don't understand anything yet, go back and understand A, then try your best to understand B and C, and then try your best to understand D. But for E, it's a little bit trickier. You have to definitely understand what B is. Okay, let's go through this. We'll try the direct method first of all. Okay, again, we're choosing first, and we're choosing second. Okay? Now, I'm not going to pick a pair, which means, well, how many pieces can I pick first? Well, there's no pair established first, so it's the same as the previous question. I could pick any piece, any of the 12. Doesn't make a difference. Now, if I'm not going to pick a pair, there's one that I could pick in this place, but there's 11 in total. One of them will make it a pair. I don't want it to be a pair. I want it not to be a pair. So if there's 11 pieces that are left for this choice, but one of them makes it a pair, like it did here, then I want everybody else. And so rather than that one piece out of the 11, I take the 10 out of the 11. Because if I pick a bishop, white bishop or black bishop, I could choose any other one of these pieces. If I pick the bishops, I just can't pick the other bishops. You'll notice that there's 10 other pieces that I could choose from that make it not a pair. 12 times 10, 120 ways. Okay, and it's a little tougher to do. What you'll also realize if you look at this carefully, I'm going to pause just in case you have to rewind and check that out again. But what you'll also notice is this is a pair and this is not a pair. I either choose a pair or not a pair. You can't choose neither of those. It's either a pair or not a pair. What you'll notice is a pair, there's 12 ways, and not a pair is 120 ways, and there are 132 ways in total. Notice that these two guys add up to give you that. Okay, a little bit tricky. A little bit tricky. Now I'm going to show you the indirect method in our next lesson after we do some homework questions. And this homework's going to be tough. You have to try your best and struggle through it and do what you can with it. Okay, and certainly ask me to take up questions and then we'll learn from there. And in this unit, you're going to do a lot of learning while you're doing your homework. Let's try probably the most complicated out of all of them, part F. How many ways are there to select a piece that's not a bishop and then a bishop in either order? Okay, well, first of all, remember, we still have a first that we choose and we have a second. Okay, and I want to select a piece that's not a bishop and then a bishop. Okay, in either order. So I'm going to make the bishop first and then not the bishop second. Or we have the scenario of, again, first and second. But in this case, it's in either order. So if I chose a bishop first and then not a bishop and a bishop, okay, then I could try the other way around. This could be not a bishop and then bishop. Okay, and then we have to decide, well, which one of them is correct? Is one correct? Is the other one correct? Are they both correct? And if they're both correct, what do we do? Okay, so first of all, how many bishops are there? There's 2. How many not bishops are there? There's 10. Simple. How many not bishops are there? Still 10. Right? How many bishops are there? 2. So this is going to be 2 times 10, or 20. Or this is going to be 10 times 2, or not much different, 20. Which one of these is correct? Like they said, in either order. This is one order, bishop first and then not the bishop second. This is the other order, not the bishop first and then the bishop second. Which one of these is correct? Well, this is definitely correct. Not a bishop and a bishop. This is definitely correct. Bishop and not a bishop. What do I do when it's an or? Do I multiply the 20 times the 20? Like I did for my fundamental counting principle? Am I doing this and this? No, it's either this or this. So the or seems to be a different idea. The or actually means this or this, which is, of course, addition, because you could have one situation or the other situation and both of them work. Okay? And so as a result, we add those together. That's our second fundamental counting principle. It's called our additive principle. Okay? Now, we have to define something called a mutually exclusive event, which is just basically things that don't happen together or can't happen together at the same time. You can't have a bishop and then not a bishop and have a not a bishop and a bishop. It's either one way or the other way. You can't have it any other way, right? There's no piece that can be a bishop and not a bishop at the same time. And so these would be called mutually exclusive. Having a bishop and then not a bishop, and then having not a bishop and a bishop, mutually exclusive. Okay, they don't cross over. If we do a Venn diagram, they don't cross over. There's no common area in there. So the additive principle is, if these two events are mutually exclusive, and it's one of these or another one of these, we add them together. Okay? And this next problem is kind of designed to illustrate that. Remember, we could have had bishop and then not a bishop, or not a bishop and a bishop. And we actually call this the or rule. Okay, the or rule. One or the other. Okay? So this is kind of a way for us to see the or rule and the and rule put together. Okay? So here's the scenario. You're on a ship and you can send messages to another ship by waving a flag. You have 4 different flags, a red, a green, an orange, a black. Okay? How many messages can you send if a message must use at least 2 flags? So it's kind of like you're sending words or making sentences with these different flags. Maybe red means stop, green means go, orange means, I don't know, caution, and black means danger. I don't know. But you can send a sentence, stop, danger, or stop, slow down, danger, then go, or something like that. And you would have to put them in a different order. Okay, or you can think of them as letters in a word. It doesn't make a difference. But the order that they're in makes different sentences. Okay, and if that's the case, or different messages, then it's going to be an important idea. Just like when you put sentences together with words, or when you put words together with letters, you have to put them in a particular order. Otherwise, it's not going to make sense. If you mess up the order, it may not make any sense to you anymore. Okay? So let's map this out. I must use at least 2 flags. So I'm going to start with a 2 flag message. Now remember, we have 4 flags. So in the 2 flag message, we're going to have something in the first spot and the second spot. Maybe I'll erase that. And I'll put the word and. Okay, so my number of ways is going to be something in the first spot and the second spot. Now I've got 4 flags, so I could use any 4 in the front there. But once I use up a flag, I don't have any more flags that are left over. So let's say I put the red in here. That means I've got 3 flags left over. Okay? If I start with a green, that means I've got the red, the orange, and the black left over. If I start with an orange, I've got the red, the green, and the black left over. If I start with a black, then I've got the red, green, and the orange left over. So 4 and 3, or 4 times 3, which is 12 messages that are different. And we can actually count them out if we wanted to. It would take us forever. You could go red, green, red, orange, red, black. Okay, that's 3 messages. And then you can go green, red, green, orange, green, black. That's another 3 messages. And then you can go orange, red, orange, green, orange, black. That's another 3 messages. Where am I at, though? 9. I can't do that with my finger. 9. Okay, and then I can go black, red, black, green, black, orange. Okay, that's another, 12 messages. Okay, and you could list them all out if you wanted to. For the 3 flag messages, it may be a bit too difficult for us to do. But that's how you do the 2 flag messages. Okay, so first spot and the second spot go together all together. And because they're all together, this spot and this spot that create a message, there's 12 messages. Let's try 3 flag messages. Remember, they said must use at least 2. So we could have 2 or 3 or 4. We can't have any more than 4 because we only have 4 flags. Okay, so the number here is equal to first spot and the second spot and the third spot. Again, it's a 3 flag message, so we need to have 3 spots. We have 4 flags to use in the first spot, 3 in the second, 2 in the third. And we got 1 left over, but we don't want to do anything with that. Okay, now it's 4 and 3 and 2, which is 4 times 3 times 2, which is 12, 24 messages. Now, you could go ahead and figure that out if you want to list them all. It would take you a little bit of time, but you could do it. You can go red, green, orange, red, orange, green. You can go red, black, green, black, red, orange, black, red, black, orange. It's just too many. So 24, you got to use the fundamental counting principle, or we'd have to use a tree diagram. Okay, and that's a 3 flag message. Finally, we have a 4 flag message. I got to go a little bit further past the homework here. And a 4 flag message, we got the first spot, and the second spot, and the third spot, and the fourth spot. Okay, and we can put 4 flags in the first spot. In the second spot, we can put 3. In the third spot, we can put 2, because we're running out of flags as we go along. In the final spot, we only have 1 flag left over, so whatever's left, that's the one that goes there. Now, you may say to yourself, well, what if I filled the last spot first? You could put a 4 there, and then a 3, and then a 2, and then a 1, or a 4, then a 2, and a 3, and a 1. You could do it in any order you want to, because remember, what we're doing with these numbers is we're taking all the possibilities and we're multiplying them. It doesn't matter if you go 4 times 1 times 3 times 2, or 4 times 3 times 2 times 1, or 2 times 3 times 4 times 1. It doesn't matter the order. In the end, you're still going to get the same number, which is another 24 messages. Now, 2 flag messages, viable. There's 12 of them. 3 flag messages, viable. There's 24 of those. 4 flag messages, viable. There's 24 of those. So how many messages can we have for at least 2 flags? So for at least 2 flag messages, how many messages could we have? Well, we could have the 2 flag, or the 3 flag, or the 4 flag messages. And what do we do with or? Well, the 2 flag, remember there's 12 possibilities. For the 3 flag, remember there's 24 possibilities. And then for the 4 flag, there's also 24 possibilities. So how many messages could we send in total that are at least 2 long? Well, they could be 2 flag or plus, 3 flag or plus, and you can't be a 4 flag message and a 2 flag message at the same time. You're either one or the other. So we add all these up and we end up with 60 messages. So as a final result, therefore, you could send 60 messages, different, with 4 flags, as long as they were at least 2 flags long. If you want to know how many messages you could send in general, you just have to do the case for 1 flag and then you'd add them all in here. Okay, so that's a good example of the multiplicative principle. You know, where it's 1 flag and another flag, or 1 flag and another flag and another flag, or 1 flag and another flag and another flag and another flag. It's and means multiply. Or it could be the or situation. And that's when we sort of compile all our results together for separate circumstances and add them all up. Now, this is a tough unit, so I want you to give it a try. Give this homework a try. There's a lot of homework to do. Each question that you'll do, you'll become better and better and better at this. Okay? Try to use this principle, these ideas. I'm going to start introducing the whole idea of elements and arrangements and things like that. But for now, I just want you to sort of muddle through it and do your best. Once we get past that, we'll go a little further with it. Okay? Ask me questions. That's key. We're going to take up questions over and over and over again. You got to do this work. If you do this work, it's going to be easy. If you don't, it's going to get pretty difficult pretty quickly. Okay, there we go.